はい。
All right, so it's a pleasure to have Professor Masahito Hayashi, which is now with the Chinese University of Hong Kong, the Shenzhen International Quantum Academy, and the Nagoya University, to give a talk about some results he had with collaborators Hiroyasu Tajima and Kosuke Ito a few years back about finite-size effect inefficiency of heat engines and quantum systems. So if someone has questions, I would ask to put in the chat, and then I will moderate. Thank you very much. Please go ahead.
Hello, everyone. Thank you for a nice introduction. Today, I want to talk about our old result about finite size effect in efficiency of heat engine in quantum systems. So, firstly, I want to explain this important fact. This is classical thermodynamics and quantum thermodynamics. So there is a big difference because in the case of classical thermodynamics, entropy is defined by operational way. So entropy is defined as an operational quantity. So this is a big point in the case of classical thermodynamics. But in the case of quantum thermodynamics, entropy is defined as maybe by using the von Neumann entropy. But as you know, von Neumann entropy is very formal quantity. So without considering the operational meaning, we can define von Neumann entropy. You can easily define von Neumann entropy by using the Torres law log law, minus Torres law log law. So this is very formal. And usually we also consider efficiency of heat engine. So that concept is always operational, even in the classical and quantum case. This is very operational quantity. So there is some big difference. So in the case of classical thermodynamics, second thermodynamic law is related to operational concept because entropy is defined as a very operational way. So then classical second law is law for operational quantity. But in the case of quantum thermodynamics, we also have a second law. Many people prove the second law, but this one is related to the formal concept. So then there is a difference. The meaning of second law is completely different in the case of classical therm and quantum thermodynamics. So, but efficiency is defined in the classical case. Efficiency of heat engine comes from the second law. So, because why this is possible? Because efficiency and entropy is both defined in the operational way. In the case of classical thermodynamics, then the evaluation of efficiency comes from the second law. So, in this sense, second law in the classical therm is very important. However, in the case of quantum thermodynamics, efficiency of heat engine does not directly come from the second law because efficiency is operational concept, but entropy is formal concept, not operational. So due to that reason, you cannot directly derive the bound for the efficiency of heat engine from the second law in the quantum system. So due to that reason, studying the efficiency is more important in quantum thermodynamics. This is a big difference from the classical case. But many people emphasize that, many people prove that second law in the quantum thermodynamics, and that person implicitly consider that the second law in the quantum thermodynamics has the same meaning as the second law in the classical case. But the meaning of second law in quantum thermodynamics is different from second law in classical thermodynamics in this way. So because I want to repeat, so this one is directly related to the operational quantity, but in the quantum case, this one does not relate to the operational quantity. This is only related to the formal one. So then we need to evaluate heat engine independent, separately from the second law. Of course, somehow this is related to second law, but this one does not come from the second law of quantum thermodynamics. So today we want to discuss studying the efficiency. This is more important. So what is the efficiency in quantum? But somehow the definition is common. So there are two bases. One is a high temperature bus. This is bus 2, and low temperature bus is bus 1. And we often define in this way. So there is a difference of energy. So the loss of internal energy is considered as a battery because we have a conservation law for energy. So due to that reason, the loss, the difference, because this one should be minus. So this one produced this heat, and this bus produce heat, but this one receive this heat. This one, in this case, this is minus quantity. So that quantity can be considered work extraction. And efficiency is defined by in that way because all of this heat cannot be converted to work because we have a loss in this part. So due to that reason, we want to consider ratio between the amount of extracted work and heat from the high temperature bus. So this quantity is called efficiency. So of course, we want to optimize this efficiency. So now I want to explain our contribution. In that topic, we have two steps of contribution. First step, I have this paper with Hiroyasu Tajima many years ago. So initially, we have an archive version in this year, but later we have a very long discussion with reviewer or something. So then we could publish this only in this year. So in this paper, we discussed the derivation of efficiency with finite size effect up to the second order correction. So this is our contribution. So we need to care about the finite effect. And buses are treated as a collection of the independent identical distributed particles. In this paper, we essentially assume that IID condition. So this is problem. And later, maybe this paper is published maybe after our archive. So this authors also consider derivation efficiency with finite effects, but as a limit, they consider only recover the kernel efficiency, optimum efficiency. They did not consider second order, but they consider finite effect in some sense. After that, they take a limit, some dynamic limit. And this paper also consider IID assumption. And this paper has a difference from ours. So this paper consider multiple conserved quantities, not only the energy, also they consider number of particles. Then we have a second step of our contribution. So in the case, in our paper, this one is after that, this guy, Gurianova's paper, we published this paper. So in that paper, we consider a derivation of efficiency of finite effect up to second order. So this is similar to previous one. And we did not consider IID assumption. We treat the asymptotic extensivity without considering the IID assumption. So because in the usual physical system, it cannot be considered as a collection of IID particles, because we have some correlation or more complicated system. For example, ideal gas in the some or fermion gas on the some limited space. That gas cannot be considered as IID particle. So then we need to remove IID assumption to address the realistic situation. This paper discusses that problem, and also we consider multiple conserved quantity in this way. But by the way, so I forget an important issue. So in our study, we consider isolated system. So the whole three system, or maybe for one high temperature bus, and this is working body, and low temperature bus, and battery. So these three four systems are connected to each other, but all of four system isolated from the other system. So we consider that assumption. So due to that reason, we cannot use summary operations. After our paper, Tube and Tomamecher and Korubeoka, they consider similar finite size collection. But the largest difference of ours, they employ summary operations. So then they cannot address the isolated system. So the whole system treated as a summary operation in their paper. So this point is different from our paper. So this is the difference between the IID assumption and general asymptotic situation. How to say this one? Asymptotic extensivity. So our setting is asymptotic extensivity. So initially we consider that kind of IID case, but our situation in this way, so we cannot do the IID assumption. Also, we often consider multiple conserved quantities. So previously, this is only one quantity, but we also consider quantity A and B. So this is a very complicated situation. And also, we have another contribution. So this paper also with Tajima, we consider we make a formulation of the work extraction process with measurement process. Sometimes this one can be considered instrument. That kind of work extraction process cannot be written as a unitary process, because in order to understand or recognize the amount of extract work, this one must be a measurement. Without measurement, people cannot recognize the amount of extracted work. So due to that's the reason we have to introduce to use of the measurement process for work extraction. But in our setting, we found that this combined system can be written as a combination of unitary and measurement. So due to that reason, essentially it is enough to address the unitary. So this kind of problem is slightly complicated, but in this talk, essentially we use unitary evolution to describe the work extraction process, because this one can be written as a unitary and measurement. So then initial part is written as a unitary, and later we need to introduce measurement. After this paper, several important papers published. Professor Tasaki also followed that topic in this way. So, and this paper also, this both papers cited our original version. So this paper somehow related, or maybe this paper, the main message of this paper is quite similar to ours, but their title is much more appealing, no-go theorem. So, but in our paper, we cannot use this kind of strong word because reviewers do not agree to strong word. So, due to that reason, we have a very serious problem. So, our message somehow much weaker than theirs, because we are not allowed to use this strong word at that time. So today, this is the organization today's part because today we don't discuss this part because this is also complicated part and we don't have enough time to talk everything. So then we do not discuss this issue. We only discuss the efficiency part. So first part is this one and the second part is this one. But today's organization is different. So this paper handle a very general setting. So then it is enough to explain the contents of this paper, second paper. But somehow the top result of this paper is too complicated, not so easy, because this one discusses a non-iid setting with two conserved quantity with finite effect up to second order correction. This is too difficult. So then in the first part, we consider only one conserved quantity. So because if we have multiple conserved quantities, the handle treatment becomes very, very complicated. We want to avoid that situation. So then we discuss this one, but still in that case, we have non-iid setting. So then this case is not the same as this one, because in that case, we discuss the problem setting with iid case. So this kind of discussion, no paper discuss this case. Of course, this case considered as a special case of the second one, but no paper discuss this one. But I think this kind of description very nice to understand that problem, because initially we discussed this one, but somehow we have a very complicated treatment to handle the finiteness, and also the treatment in this paper strongly based on the iid assumptions. But that kind of iid assumption is not essential in this work. So this derivation is much more elegant. So then, firstly, we introduce this one. And second, we extend this result to the two conserved quantity case. This kind of generalization is maybe not so difficult. But if you study this one in beginning, maybe you have a very big difficulty, because the situation is very, very complicated. And later we explain lower bound. Lower bound means that we concretely construct our work extraction process to achieve this upper bound up to the second order. This construction part does not appear the difficulty of the this multiple conserved quantities. So then we explain this one here. Of course, if we discuss the detail of that discussion, maybe quite difficult, but we will skip that detail part. And also, I explained some application. One is that Ising spin chain, one-dimensional spin chain. This one is not iid case. This is somehow correlated one-dimensional spin chain. In classical sense, this one can be considered Markovian chain. So this is an interesting example for non-iid setting. But somehow this is similar, slightly similar to iid setting, because in the classical case, Markovian process is quite similar to iid case. And the second example is more interesting, because this is free fermion. This is very far from the iid setting. Still, our general setting can accept this very general setting. So this is the organization today's talk. So from the next slide, I will proceed to the more concrete topic. So do you have any question or comment until this part?
I do not see anything in the chat. I think you can proceed.
Okay. So then I start with the one conserved quantity case. Yes. So this is the one physical quantity. Maybe this is energy, and this is energy, and this is high temperature bath, and this is low temperature bath, and that's the difference. The loss of this one is considered as heat. This heat can be considered minus, and this is plus heat. And we have this work extraction. This is our setting, and this is a working body. Sometimes this one is called catalysis. So in this case, we often assume this because second law is needed. So in order to derive the efficiency, in some sense, we need the increase of fundamental entropy. So due to that reason, we need some assumption. So this is bus, and this bus identity operation should be preserved for this time evolution in this way. And cyclicity. So cyclicity means that the Roshi means that the state of the state of the working body, state of the catalysis. This one should be preserved. We assume this assumption. So then,
can I ask you? Excuse me? Can I ask you something about one slide before? One more before. Okay. So this delta QA. So these two quantities A1 and A2 are two observables, right?
Yes.
So this delta QA is the change in the expectation value of this observable A1 and A2. Is that correct?
Yes, change, yes.
Okay, thank you.
So later I will give its definition more precisely. So then we need a formulation. This one is yes. So this is inverse temperature. So this is system 1 and system 2, and the inverse temperature we have this way. And this inverse temperature considered as a parameter to describe our state. So we have this state, and lambda is somehow scaling parameter because we want to consider some dynamic limit. So we need to introduce this one. Of course, in the case of IID assumption, usually we have n. N is a number of particles, and n considered as a scaling parameter. But now we want to consider more generic situation to include the ideal gas or gas in the some confined space. So that kind of case, sometimes lambda considered as a volume of that system. So we want to consider that parameter, scaling parameter. So based on the scaling parameter, we can define this free entropy, some potential function in this way, and we can define thermal state in this way. And if we have an index 0, this one considers the initial value of that parameter. So we assume that initial state is thermal state. And we have asymptotic extensivity. Asymptotic extensivity is the following. So we have some lambda, and lambda become very large. In that case, we have this kind of approximation. And also, we have this one, expectation value. This is somehow related to the information geometry. So information geometry is a very powerful tool to handle this problem. But this relation is not sufficiently focused. Once we have this one, so we define this convex function. This is convex function for theta. And once we have this convex function, we can define expectation value, this expectation value, but this expectation value can be described by the minus of the partial derivative in this way. And also we consider that correlation by considering this one. So if we consider some information geometry, so in that case, this kind of second derivative called by Fisher information matrix. So this one is always positive semi-definite because this function free entropy is a convex function for theta. So we have this notation, and we have a second law conserved quantity. So second law is this one. So from that property of the some dynamic process, we have this inequality. So first one is this one, and this one is always greater than relative entropy of two density matrix. This is the final state. This is not generally. This is not thermal state, but initial one is thermal state, and the final one is not thermal state. And this one is a difference. We have this physical quantity and this one. The total of sum of two quantity energy should be preserved, but each system does not preserve this quantity. So we have this difference. We have this difference. We have this one. And as you know, from this inequality, this relative entropy is always positive value, not negative. Sometimes zero, but this is always not smaller than zero. So then we have this inequality. This is some dynamic constraint. So
can I confirm? So this delta A is what you wrote before as delta QA. Is it the same?
No. Maybe signature is opposite. This is the relation.
With a minus, you mean?
Minus, yeah.
But okay, but it is basically the same thing. Okay, thank you.
So due to that relation, we have this one. So amount of work extraction is defined by in this way. So then, using this inequality, we can, and this definition and this inequality, we have this one. So this is upper bound. This coefficient is called Carnot bound. This coefficient can be considered efficiency, thermal efficiency. So unfortunately, of course, this inequality implies this inequality, but equality can be achieved only in the thermodynamic limit, because this inequality is not tight in the finite length regime. So in the case of finite length regime, we cannot attain the equality. So only in the thermodynamic limit, we have an equation. So then we should focus on how the relative entropy can be small under the fixed heat amount in the finite regime to incorporate the finite size effect to Carnot bound. And this is maybe we repeat the same thing. So because this kind of quantity can be considered as quite small, so depending on lambda, so in that case, maybe we can ignore that kind of finite length correction when lambda go to infinity. So then we can recover Carnot efficiency. But usually this heat is somehow not so small. So we want to consider finite length efficiency. So firstly, we define entropy in this way. So entropy can be considered as this kind of Legendre transform of the this potential function. So then we can obtain this entropy, Pohnman entropy. So the difference of Pohnman entropy can be described by this way. But now we need to emphasize that the theta dash is so I forget this one. This is the final state. But usually final state is not equal to the thermal state. So then, depending on that final state, we can choose that temperature such that the expectation, yes, this expectation is the same as this one. So we need to temperature such that the average of that physical quantity is equal to average of the this final state, physical state under this final state. So in this way, we need to choose this inverse temperature. In some sense, this is ideal state. Yes, this is ideal state, and this is a real state. So real state is not a thermal state, but we choose some ideal thermal state such that their physical quantity is same as the this final state. So considering this way, we have some discussion, and we have this way. So then we have this kind of second order correction. So using that discussion, finally we can obtain this second order coefficient in this way. So this part we make some calculation. Certainly this is difficult. This is complicated. But based on that calculation, we have a second order correction in this way. So this coefficient is defined by this one, but this coefficient comes from the previous discussion. This is the derivation of the second order correction in the case of one conserved quantity. So that kind of discussion essentially same as the first step of our paper of this one. So in that paper, we derive this one. But in that case, we assume that IID assumption in this. So we have some coefficient C1 and C2, and we have this. But in our current discussion, we have only this one. This one corresponds to here. But in IID case, we have we could derive that this coefficient. This is a higher order term. So to derive that this one, we need a more complicated analysis. At that time, maybe our analysis depends on the property of IID assumption here. But that C1 is the same as this CAA, this one. So this is the case with one conserved quantity case. Now we want to proceed to the two conserved quantity case. Do you have any question for this part?
Maybe I will ask you later.
Okay, thanks.
Thank you.
Then now we have proceed to the two conserved quantity case. That seems more complicated, but somehow I believe that quite difficult to understand this two conserved quantity case without considering the one conserved quantity case. So now you are already prepared basic knowledge about the one conserved quantity case. So then maybe you can easily understand two conserved quantity case. So in that case, we have a second quantity, B, yes, B1 and B2. So there is two bars, and these two bars have another physical quantities. But our energy is only first quantity. Our work extraction only for the first quantity. This one is somehow difference of the this one and this one. The sum of difference. Sum of A1 and A2. So this one is changed during that process. Work extraction process, the sum of A1 and A2 is changed. That change is written as this. So yes, so then we explain. So we have two kind of quantity, but in order to simplify our notation, we introduce this quantity x1 and x2 is a1 and h, and x3 and x4 is b1 and b0. We introduce this notation because in order to save the space, we want to handle these four quantities in unified way. So then we need this notation. Sometimes this is very complicated, but without introducing this notation, we cannot explain efficiently. So then we need this notation. So now we define thermal state, generalized thermal state, because we have this quantity. Sometimes B considers the number of particles. So in that case, if B is number of particles, then gamma corresponds to the chemical potential. Chemical potential, I think. So beta is an inverse temperature. But we want to handle this problem unified way. We introduce one sequence of the parameter in this way. So theta 1, 2, 3, 4 corresponds to beta 1 and beta 2, gamma 1 and gamma 2. And maybe we will handle this one as x1 to x4 and theta 1 to theta 4. So in this way, we can define this in a more simple way. So now we already consider that notation. That x is 1, I run from 1 to 4. So sometimes this is A, sometimes this is B. So we have a four parameter, four quantities. So then this is free entropy. We have this extensivity in this way. And also that expectation value is described by the partial derivative of this potential function. This is a very common method in information geometry. And we consider a second derivative, then we can define Hessian information in this way. So thanks to the extensivity, this J can be written in this way. So then we have a generalized heat engine in this way. So then we have a conserved law in this way. So this one and this one. And general heat can be considered in this way. And amount of work extraction is written as in this way. This is quite important. So our focus on this one, we want to evaluate how much we have this work extraction. And of course, we have a similar assumption. This is completely same as the previous slide. No difference. So then from that kind of assumption, we obtain the increase of a phenomenon entropy. This is the kind of second law. Based on this formula, we have this inequality. So this means that we have, of course, later we use this one, xy, in this way. So sometimes we use this notation xy, sometimes we use a, but this one handle more unified way. And this positivity of relative entropy implies that this inequality. This is a thermodynamic constraint. This inequality is very important because this inequality, using this inequality and this definition, we can derive this one. Because similarly, we can solve this quantity by using, you can solve this one. So then you have A1 can be written as a linear sum of W and A2, and then this A1 input this one. So then we have some relationship between the WA and other physical quantity except for A1. So then solving that inequality, we have this inequality. So then we have this upper bound. This one is called the generalized cardinal bound because we have an additional term. So then we have to consider finite size effect in the same way. Of course, this inequality implies this upper bound for amount of work extraction. And similarly, this strict inequality is very serious. Usually, we cannot realize equality due to the finiteness of the our system. So in order to achieve the equality, we need to consider some dynamic limit in the same way. So then, similarly, we have this discussion. So maybe we assume this one. So to derive the more efficient discussion. So then finally, we have a form of the polynomial entropy by using this way. This is Legendre transform. By using this one, we can derive this inequality in the same way. But here, we need to define the inverse temperature. But this is not only inverse temperature, but this is including the chemical potential, because now we have a 4 parameter. So this is I equal to 3 and 4 correspond to the chemical potential. This one. So anyway, this parameter is important. We need to this parameter in the same way as previous. So we need to choose this parameter such that the average of each physical quantity equal to the average of under this final state. In this case, final state is not thermal state, but we need to choose ideal thermal state such that their physical quantity is same. So then, using this discussion, we have this kind of evaluation. Then we have this inequality. We have this one, this inequality. This quantity is upper bounded by this one. So using these two quantity, so we have this inequality in this way. So then we have so many complicated coefficients. This one is the previous one, but also now we have a physical quantity B, B1 and B2. So due to that reason, we have this additional term. This is cross term, and this is A term, and this is B term in this way. So we have a more complicated term in this way. So in this way, we can derive this upper bound in this way. So this is very complicated in this way. So this part and this one is derivation of the upper bound up to the second order correction. In the remaining part, we discuss how to achieve this lower bound and on upper bound. How to achieve this upper bound, but by constructing our operation. Maybe we need to explain battery system. So usually it is enough to explain derive the unitary process including a battery system. Then later, after a unitary process including a battery system, we make measurement on the battery system. Then we can realize the work extraction. This is our story. So due to that reason, it is enough to construct a unitary process including the battery system. So we have now we proceed to the achievability part, but I'm afraid maybe you have some question or comment for upper bound part.
So maybe I can ask you something now. It's Francesco speaking.
Yes.
So I wanted to understand better somehow the philosophy here. So you still define work as the difference, well, with a minus sign, as the sum of the change in the expectation value. Okay. So do you understand? So the work is defined as the change in the expectation values of these two quantities. Okay. So in which sense exactly you say that that inequality is not tight in the finite size case?
Of course, in the finite space, this is not tight, yeah. We have this upper bound, but this inequality is not tight in general.
And this comes from where? Is there an equation where I can see exactly where this comes from, this non-tightness in the finite size case?
From this one.
So it's the strictly greater than zero part.
Yes.
Okay. Okay, thank you.
So can I ask a question? So can I see the main result, your main result?
There is a two main result. First,
yeah.
This is one conserved quantity case.
Okay, so I would like to understand the finite size effect term. So I would like to know, so what is the size in this term? So
This is this one and this one.
Okay, so CAA includes so CAA includes the size of bus or not?
CA is constant. CA is constant. This
Okay,
is
okay, I
constant.
see. So
This is constant.
okay, okay.
This lambda is a scaling parameter. Lambda is a scaling parameter.
I see,
This
I
is
see.
corresponding.
Okay, so lambda represents the size of the bus. I see. Okay. Thank you very much.
So this is another version. So this another version divided by delta Q. So and lambda replaced by n. So then we have this. This and this is almost same. Lambda replaced by n and divided by delta Q in the both sides. Then we have this one. Sometimes we use this notation.
Okay, okay. I see, I see. Thank you very much.
Maybe this is very complicated, I think. Then this is a two-particle case. Two-particle case is more complicated. So to derive this one, so that relative entropy is essentially equal to the this difference of the phonome entropy. Relative entropy is very close to phonome entropy. So then we need to consider this kind of correction this way. So then we have this one. This is too complicated, I think. Then now we are considering the how to construct our process. So now I explain that it is enough to construct unitary before measurement. So then we construct unitary in this way. So firstly, we have a conservation law. Conservation law is written as this way. This one should be commute. And cyclicity should be this one. So then firstly, we introduce ideal initial state. Ideal final state. Ideal final state is the following. So the difference should be equal to this. This is ideal. Ideal sum state. Of course, if we replace this one as the real final state, we have this equation in the same way here. But this equation does not hold, I think. This equation does not hold, but this one should be hold. Yes. So then, then we need to explain our protocol in that way. So the difference is the following. So this is the initial state, and this is ideal state. Ideal state and the initial state has a common. Now we are considering commutative case. Commutative case means that all observable, all physical quantity should be commutative. A and B and A1 and A2 and B1, B2, everything should be commutative. So this is somehow strong assumption, but somehow due to that reason, we have a common eigenvector in this way. So then our difference is only the eigenvalue. So this is eigenvalue. Eigenvalue forms some distribution in this way, and also another eigenvalue. This is the ideal eigenvalue of the ideal final state, and this is eigenvalue of initial state. And we have true initial state. No. We have true final state. This is true final state. Of course, we have only unitary operation. So then eigenvalue of initial state and eigenvalue of final state has the same value. So this eigenvalue and this final state of eigenvalue is same. So this means that maybe this one is only the we have a change of the order of that eigenvalues. So then we have a final state. But this is the ideal final state. So we consider summary state. So then this amount and this amount is not same. This is different. So this is some problem. So we need to consider that the difference between that ideal summary state and true some final state. Our M is the difference between the two states. So in the remaining part, the M of the remaining part is the following. Only we evaluate the difference between this true output state, the true final state and ideal final state. We need to discuss the difference. That difference is quite difficult to be handled. It is not so easy to handle that difference. We need to introduce very complicated mathematics to handle that problem. Anyway, we have this diagonalization and we have that conversion. So our unitary can be considered as somehow only the conversion on the eigenvalues. We only change some eigenvector. So this one can be considered our protocol. So and also this one is, I'm sorry, so this is non-commutative case, but I want to skip this one. This is too difficult. This is too difficult. And to achieve the that's one achievability, we need some assumption, but some technical assumption for the excessivity. So we have this good order evaluation. And also, we need to some small assumption. So this is optimal output, and this is ideal one. That difference quite small. We need this some assumption. This is no. Previous assumption. By using the previous assumption, we have this evaluation. This one and this is quite similar. So finally, we want to evaluate that difference between this one and this one. So not so easy to evaluate this one, but to evaluate this problem, we need to use some information dynamic method in this way. So because we have that kind of Pythagorean theorem in this way. So then this quantity can be evaluated as some other quantity in this way. So this is another summary state. We introduce some another summary state, and the difference between this and this one is lower bounded by a difference and difference between these two quantities. So using the this lower bound, so we can finally obtain the this kind of difference of the expectation value in this way. So then this one is quite small. So finally, yes, we could prove that this quantity is equal to this one. But the derivation of this evaluation is extremely difficult because we need to introduce very difficult mathematics, strong line deviation. This is extremely difficult mathematics. And this one is a brief sketch of that idea of very difficult mathematics. But to fully explain that this one, we need to discuss more than 3 or 4 page equations. Very difficult calculation in this part. So then this is some idea of this part. So essentially, the key point of this one is derivation of this one. This relative entropy is quite small around this order. So this is most important to achieve the to achieve that upper bound. This is the end of that achievability part. So do you have any question? This is optimal by constructing some order change of the this one, and this is the ideal. So our unitary operation is maybe yes. Eigenvalue is somehow same, but we need to change the eigenvector in this way. So then this state is very close to this one. We need to change order of the eigenvectors. This is our unitary operation. So using that change of our eigenvector, so then that final state is very close to the ideal final state.
Do you also have to change the order? Like you have to reorder eigenvalue?
Okay, yes, only by changing the order of the eigenvectors, yes.
So that's also one of the reasons why it is not conservative, strictly speaking.
I cannot understand. Conserved?
So such a unitary, I think in some slide it was written that it does not satisfy, it does not preserve the conserved quantity. Or does it?
Wait. そうか。conserved quantity order? それはそうかな。wait. それどうしたっけ ちょっと待って。
The conservation law is satisfied for the in the total system, including the battery.
Oh, okay.
Yes, including, but so, yeah. So
Thank you.
that difference is somehow moved to the, yeah, battery, yes, yeah.
Thank you.
Thank you. So then difficult part. So by using this complicated analysis, finally we derive this. So then it is the problem reduced to the case with the ideal summer state. Because in order to derive that upper bound, we only consider the case with the ideal summer state case. So then it is enough to show that the difference between the true final state and ideal final state is quite small. So then we could derive that lower bound in this way. This is ideal. But of course, the derivation of this equation is too difficult. Maybe total page length looks like more around 10 pages, maybe. I don't know. Because I checked the document again, but some final part around only 4 pages. But in order to proceed to that final part, we needed to make a very long preparation. So this one more than 5 pages, maybe total around 6 pages, 10 pages in the PRE format. So the derivation of this part is too difficult, extremely difficult. So if you don't have, yes, somehow in order to, the key part is this, so we need to count the number of this element. This is the initial state and this is the ideal final state, and we need to count this number, and this number should be written this one, and this one should be considered the log of this one. But in order to count this number, we consider the uniform distribution. If we consider uniform distribution, then this number is considered as a probability of this set. Because the uniform distribution case is almost the same, only the constant times of the number of elements. So then we apply standardized deviation for the case of uniform distribution. Then we have this kind of expansion. This kind of expansion is quite important. So then I want to proceed to some example case. Can I go to the this example part? So in this case, we have a scale parameter n. So because this is only one dimension spin chain, this is very close to the IID case. We have only integer scale parameter, and this is Hamiltonian in this way. And we consider this function phi in this way. And this is the potential function. Once we obtain that potential function, we can calculate everything in this way. So, because we have that general formula, but general formula, everything comes from the potential function. Once we have that convex function, potential function, then we obtain so many kind of Fisher information and several quantities. But everything comes from the that derivative of that function phi. So then we have this first order. First order is current one, and the second one is this one. Second order correction is this. This. And the second example is more practical. This is maybe some gas, fermion gas, free fermion gas inside of the one-dimensional well potential. This way. But in that case, we have this one. We have this, and lambda is some scale parameter difference between the two well. And we have several quantity. One is yes, Hamiltonian. This is energy, and another one is n. N is number of particles in this way. So the total of number of particles is constant among the two buses. This is a hot bus, and this is a cold bus, and the total number should be conserved. So then we define this potential function in this way. So we have not defined. So we have a potential function in this way, and this one has asymptotic extensivity in this way. And we have this upper bound in this way. We have several coefficients. This is chemical potential of this one. This is very famous, and maybe this is also chemical potential. These two coefficients very famous on the chemistry, I think. In chemistry, we always consider this. And we have some upper bound. No. We have some other second order coefficients in this way. These ones very complicated. But this coefficient is this order in this way. So conclusion. So we consider generic non-iid scaling for heat bath based on the asymptotic extensivity. Scaling parameter is lambda, and we made a universal calculation of the optimal performance of quantum heat engine with multiple conserved quantity beyond the iid regime. And we consider that fine-grained generalized current bound. We have a finite-size effect. Not only characterized by temperature, but also a correlation between the several quantities. Not only the inverse temperature. We also count about the chemical potential. And also we introduce the general protocol to achieve this upper bound. And we consider two interesting examples for that general model. So thank you very much. Maybe this is around 1 hour, 1 hour, 10 minutes.
Okay, thanks a lot for this very interesting talk, very insightful. So first of all, I would like to ask from the audience if there are questions. I have some, but I would like to give priority to the audience. Okay, so maybe I can start asking you a few questions. So essentially, making everything kind of very easy, like the punchline would be that if you want a process that is thermodynamically reversible, so that somehow the second law inequality is achieved with an equal sign, you need an infinite size bath. Am I correct? Like the thermodynamic
equal, but equal case is somehow almost infinitesimal small case, but usually that kind of situation cannot be realized, so maybe impossible, I think.
So like thermodynamic reversibility is a abstraction, kind of ideal case.
Ideal, yes. For example, okay, please consider following case. in the case of entangled distillation and entangled dilution, so many people previously considered that this is reversible. So, because if we consider infinite many copies, so then the coefficient is invertible. But in the realistic case, this one has some second order correction. Due to that reason, once we convert to the how to say, initial one is IID of some special one, and then this one converted to the maximum entangled. Again, you recover to the IID of special state. So in that case, we have always some loss. The loss is somehow square root n order correction. So maybe if we have no loss in the case of the first order asymptotics, but maybe we have some loss in the sense of the second order. So in this sense, it's quite difficult to say that this is reversible.
Yes, I understand.
We have some loss in the sense of second order correction.
I understand. Yes, but I mean, thermodynamic reversibility is very much an abstraction. Also, it takes infinite time usually, to achieve a thermodynamically reversible process. But so this brings me to another question. So if here you are considering like a finite bath, the temperatures that you have, what are the temperatures of what exactly?
Theoretically, in the case of one conserved quantity case, temperature is only this one, inverse temperature.
Yeah,
because
but it's a parameter. It's a parameter.
Yes,
that,
parameter.
So typically,
yes,
temperature one says there is a bath at temperature T. Like the temperature is something that qualifies the bath. So here the bath is finite and somehow kind of messy. So I was wondering, what is this parameter? It's would there be any way to estimate this parameter or to measure, or do you understand my question?
Yes, but of course we need to discuss that problem. We need so many assumptions, but one assumption is that the initial state is thermal state. So once this one is thermal state, then we have an inverse temperature.
Good. Okay. So you can imagine that first there is some kind of external reference at some fixed temperature that first achieves thermalization. Then you close the thing and you start your analysis there with that parameter somehow.
Without parameter. With that parameter. With parameter, because we assume some state.
Okay. Questions from? Thank you very much. Thank you. Questions from audience?
So can I ask some questions? So
yes, please.
So I would like to so I expect that we can also use a kind of information spectral method to analyze the upper bound of Carnot efficient Carnot bound. Is it correct or not?
I cannot understand. Could you explain who's speaking?
So
who are asking? Please introduce your name.
So I'm Shintaro Minagawa, and
yes, okay.
So
information spectrum. So
yeah, so because so in your analysis, so it is beyond the IID. So then I thought that we can also use a kind of information spectrum method, right?
I don't think so, because information spectrum method is too general. So in that situation, we don't have asymptotic extensivity. This is a very strong assumption. But this one is somehow very natural in statistical mechanics, because in the model of because in many models of statistical mechanics, they have this property. This property holds in many model of the statistical mechanics. So then I think this assumption, okay, very nice. But this assumption is much stronger than situation of the information spectrum.
Yes. I see. So, yes, I understand. Thank you. And also, so another question is about so basically your analysis based on the unitarity of unitarity, right? Unitariness, right? So
Yeah. So somehow, yeah.
I see. So I thought that some paper use a unitariness, but so for example, Skripchik's paper does not use unitarity, but it uses a Gibbs preserving. So can we also derive some inequality using the kind of
whose paper considering the Gibbs?
Skripchik's 2014 paper, I think. Maybe
this paper? 14.
For 2014, I think.
For example, they also assume this, I think. No? But their case is only summary operation. I think that assumption is summary operation assumption, I think.
Yeah.
Not isolation.
I see. Okay.
But in the case of summary operation, the problem much easier. Because the time evolution can be described by using the relation of the relation of marginalization relation. So in that case, the problem is much easier. So then their analysis is much more somehow elegant than ours. But their assumption is slightly stronger than ours.
I see. Okay. So, I see. Okay. Thank you very much.
Other questions? Maybe I have the final one. I'm sorry, I'm asking you so many questions. I hope it's okay. So I think that when people say, oh, this is like one-shot quantum thermodynamics, sometimes I notice that people have some sort of confusion in the sense that on one hand you have work like yours in which the finite size of the bath is taken into account to provide more refined bounds on the amount of work that you can extract in average. And then there are also work instead that have a kind of different approach. And instead they want to see like the worst case. So they treat work as the average of some random variable. And they want to work like with the worst case.
Worst case, because why you are considering worst case? Because you are introduced measurement, I think. This is correct?
Yes, no, it's not me. I'm just saying that there are these two kind of approaches to finite size effects or finite repetition effects on quantum thermodynamics. On one side, you can consider a finite size of the bath, but still work with average quantities. On the other side, one could also consider kind of single shot information theory or finite block length information theory on the work random variable. So these are two different things, I think. Am I correct? Or are there connections that I cannot see now? What do you think?
Random variable, yes. So, but we are considering only average and not random variable.
Exactly,
because in order to introduce random variable, we need to introduce measurement. Otherwise, we can't. Of course, our case may be considering the average value.
Good. Yes.
We ignore that expression case. But now we are considering the, how to say, measurement problem. We do not consider measurement problem. So once we introduce the measurement problem, of course we can consider worst case analysis.
Sure.
But,
I mean, it makes perfect sense. So it's an expectation value, kitaichi, no? So it's like expected amount of work.
Yes.
One would get. Okay. Yes. Thank you. Any other questions? Okay, I think so. I think that the speaker has to be very tired because he spoke for very long time. But it was very, very nice. I'm really grateful for your time, and so I would like to thank you again. And okay, so we can stop recording here.